Look up at the night sky. What do you see? For most of us, it's a familiar canvas of stars, planets, and the gentle arc of the Milky Way. But what if I told you that hidden within that seemingly peaceful expanse lies something truly bizarre, something that shouldn't exist according to everything we know about the universe? A place so profoundly cold and empty that astronomers are still struggling to explain it 2 decades after its discovery. This is the cold spot, an anomaly on a scale so vast it challenges the very laws of physics as we understand them. Imagine a region of space nearly 2 billion light-years across, colder than its surroundings by a margin that defies probability, a cosmic blank spot, an emptiness that echoes with questions rather than answers. For years, scientists have debated what could cause such a thing. Is it a void so enormous it rewrites our models of the universe's structure? Could it be the imprint of a collision with another universe? Or is it something even stranger, a clue to forms of matter or energy we haven't yet dreamed of? In this video, we're going to journey together to the edge of everything we can see and probe one of the greatest mysteries in modern cosmology. We'll explore how this cold spot was discovered, what it might mean for our understanding of reality, and why its existence keeps brilliant minds awake at night. From multiverse theories to cosmic defects, from supervoids to speculative physics, this is about more than just science. It's about wonder, it's about curiosity. And it's about what happens when the universe throws us a curveball so unexpected that we have no choice but to rethink everything. So settle in. By the end of our exploration, you won't just know what the cold spot is, you'll feel why it matters. Not just to astronomers, but to anyone who's ever looked up at the stars and felt that tug of mystery, that desire to understand just a little more about this strange and beautiful cosmos we call home. This is the deepest void in the universe, and we're about to explore what might live inside. Back in 2004, a team of astronomers was meticulously sifting through data from a very special satellite called the Wilkinson Microwave Anisotropy Probe, or WMAP. This spacecraft was designed to do one thing incredibly well: map the faint, ancient light that fills the entire cosmos, the cosmic microwave background. Think of this as the universe's baby picture, a snapshot of the heat left over from the Big Bang. As they analyzed this map, they expected to see a mostly uniform distribution of temperature with tiny, predictable fluctuations. But then they saw it, a massive, inexplicable cold patch in the constellation Eridanus. It wasn't just a little bit colder, it was a significant temperature drop, a profound chill in the cosmic background radiation that stood out like a sore thumb against the rest of the data. The sheer scale of it was almost incomprehensible. This cold spot measures an astounding 1.8 billion light-years across. To put that in perspective, if you could travel at the speed of light, it would take you nearly 2 billion years just to go from one side to the other. This wasn't just a curiosity, it was a direct challenge to our standard model of cosmology. According to our best theories, the universe should be fairly homogeneous on such enormous scales. A fluctuation this large and this cold simply shouldn't exist. It defied probability and immediately split the scientific community. Some researchers, like theoretical physicist Laura Mersini-Horton, put forward a truly mind-bending idea. She suggested this could be the bruise left behind from a collision with another universe, a bubble universe from the multiverse brushing up against our own during the early moments of cosmic inflation. On the other side of the debate, more conservative voices argued it was likely just a supervoid, an enormous region of space that is mostly empty, containing far fewer galaxies, galaxy clusters, and even less dark matter than the rest of the universe. The discovery turned this cold patch in the sky into a cosmic crime scene, and astronomers became detectives, scrambling for more clues to figure out what or who was responsible. It ignited a race for evidence that continues to this day, making the cold spot one of the most captivating and enduring mysteries in all of modern science. So what exactly are we dealing with here? This isn't just some slightly cooler region of space. It's a profound anomaly etched into the very oldest light we can observe, the cosmic microwave background. Think of this background radiation as the universe's thermal footprint, the lingering heat signature from the Big Bang itself. After that initial explosive moment, the universe expanded and cooled, leaving behind this faint, nearly uniform glow that today is just a few degrees above absolute zero. In a perfect, smooth universe, this radiation would be almost identical in every direction, but it's not. It's filled with tiny ripples and variations, which are actually incredibly important. These are the seeds that eventually grew into the vast cosmic web of galaxies and clusters we see today. Most of these fluctuations are small and fit neatly within our models. The cold spot, however, is a dramatic outlier. We're talking about a temperature dip of around 70 microkelvins. Now, that number might sound insignificantly small, and on a human scale it is. But on a cosmic scale, stretched across a region nearly 2 billion light-years wide, it's a massive and statistically staggering deviation. It's so large and so cold that the probability of it forming by random chance in our standard model of the universe is extremely low, less than 1 or 2%. For a while, some scientists held out hope it was just a statistical fluke, a ghost in the machine. But then along came the Planck satellite, a more advanced European Space Agency mission designed to map the CMB with even greater precision. Planck's data didn't make the cold spot disappear, it confirmed it. This was a real, physical feature in the cosmos, not an error. This confirmation forced everyone to take it seriously and to start proposing real explanations. The most straightforward idea is that we're looking at a supervoid. This is an almost unimaginably vast region of space that is largely empty, containing far fewer galaxies, gas clouds, and even less dark matter than the surrounding universe. The theory goes that as light travels through such a void, it loses a tiny amount of energy climbing out of the gravitational well, a process known as the integrated Sachs-Wolfe effect. This energy loss would manifest as a slight cooling in the CMB. The problem is, the math doesn't quite add up. Even the largest supervoids we've discovered elsewhere don't seem capable of producing a temperature drop this significant. It's like needing a canyon 10 miles deep to explain a shadow, but only finding a ditch a few hundred feet deep. This discrepancy has led researchers to consider far more exotic possibilities. Perhaps it's a remnant from the universe's earliest moments, a cosmic texture. This is a hypothetical defect in the fabric of space-time, a kind of knot that formed as the universe cooled and its fundamental forces separated. The unraveling of such a knot could have left a distinct imprint on the background radiation. An even more mind-bending proposal is that the cold spot is evidence of a collision with another universe, a bruise left from our cosmos bumping into a neighboring bubble universe during a period of rapid inflation just after the Big Bang. Each theory pushes the boundaries of physics, challenging us to look deeper into the data and further back in time to understand the true nature of this cosmic mystery. To grasp why the cold spot is such a profound mystery, we first need to understand the canvas it's painted on the cosmic microwave background. This faint glow is the oldest light in the universe, a relic from a time about 380,000 years after the Big Bang, when the cosmos had cooled enough for atoms to form and light to finally travel freely. Before that moment, the universe was a hot, dense fog of plasma, opaque and blinding. That sudden transition allowed light to burst forth, and that primordial flash has been stretching and cooling with the expansion of the universe ever since, now registering as a microwave whisper just a few degrees above absolute zero. This afterglow is not perfectly uniform, and that's the key. The tiny variations in its temperature, on the order of millionths of a degree, are like a cosmic fingerprint. They represent the slightest overdensities and underdensities in the early universe, the seeds from which all structure, from the smallest galaxy to the largest supercluster, would eventually grow. By mapping these fluctuations with satellites like WMAP and Planck, cosmologists have been able to construct an incredibly detailed baby picture of the cosmos, confirming predictions of the Big Bang theory, and even allowing us to measure fundamental properties of the universe, like its age and composition, with stunning accuracy. The patterns in this background radiation are so regular and predictable that they follow a specific statistical blueprint. Most fluctuations are small and confined to certain scales. The cold spot shatters this pattern. It is not just a little colder, it is a vast, extended chill that is far larger and more pronounced than our models say should be possible. It's an anomaly that stands outside the established statistical rules of the cosmos. When the Planck satellite confirmed its existence with even greater precision, it forced a critical question. Is this a flaw in our statistical understanding, or is it a real physical structure that imprinted itself on the universe at a very early time? This outlier status is what makes it so compelling. It suggests that either our standard model of cosmology is incomplete, missing a crucial piece of physics, or that we are seeing the imprint of something extraordinary that happened in the universe's first fleeting moments, a cosmic defect, a collision, or a void of such immense proportions that it challenges our very understanding of how the cosmos evolved. This single cold patch, a fossilized whisper from the dawn of time, is pushing our most fundamental theories to their breaking point. So if a supervoid isn't the answer, what else could it be? This brings us to one of the most speculative yet utterly fascinating ideas in modern cosmology, the multiverse hypothesis. Theorists like Laura Mersini-Horton have proposed that the cold spot might not be a structure within our universe at all, but rather the imprint of a collision with another universe entirely. This idea springs from the theory of eternal inflation, which suggests that our universe is just one bubble in a vast, frothing cosmic foam of universes, each with potentially different physical laws. During the rapid expansion of the early universe, these bubble universes might have occasionally bumped into each other. Such a collision would have transferred energy at the boundary, potentially creating a region that appears anomalously cold in our cosmic microwave background. It's a staggering concept that we might be seeing evidence of a neighboring cosmos in the same way a bruise on an apple hints at an impact. Of course, this is an extraordinarily difficult idea to test. Critics point out that there's no independent evidence for such a collision, and that it requires a level of fine-tuning that makes many physicists uncomfortable. They argue that it's more scientifically parsimonious to look for explanations within our own universe before invoking entirely separate realities. Yet, the multiverse hypothesis remains a powerful and captivating possibility because it directly tackles the anomaly's scale and strangeness. It doesn't just ask what the cold spot is, it asks what it might be a window into. This theory pushes cosmology to its absolute limits, challenging not only what we know but how we define the very nature of existence. But what if the explanation isn't something within our universe at all? What if the cold spot is a cosmic scar, a bruise left behind from a collision with an entirely separate universe? This is the breathtaking premise of the multiverse hypothesis, a theory that takes us to the very edge of known physics. the idea was notably championed by theoretical physicist Laura Mersini-Horton and stems from the concept of eternal inflation. This theory posits that our universe is just one bubble in a vast, endlessly frothing cosmic foam. In the first infinitesimal moments after the Big Bang, space itself underwent a period of hyper-expansion, inflating faster than the speed of light. During this frantic stretching, different pockets of spacetime could have pinched off and expanded into their own separate bubble universes, each potentially governed by its own unique set of physical laws and constants. Now imagine these bubbles floating in a grand, higher-dimensional arena. If two of them were to gently bump into one another, the energy released at the boundary of that collision would have to go somewhere. In our universe, that energy transfer could have created a distinct imprint on the cosmic microwave background, a vast circular region that appears significantly colder than its surroundings. It's a staggering thought that we might be looking at the fingerprint of a neighboring cosmos, a place with fundamentally different reality. Of course, this is perhaps the most speculative explanation on the table. The primary criticism is a practical one. How do you test it? We have no way of peering outside our own universe to look for these other bubbles, and the predicted signatures of such a collision are still a matter of intense theoretical debate. Many scientists favor the principle of Occam's razor, which suggests that the simplest explanation, usually one that doesn't invoke other universes, is often the most likely to be correct. They argue that we should exhaust all possible explanations within our own cosmic framework before leaping to such an extraordinary conclusion. Yet, the power of the multiverse hypothesis isn't just in its potential to explain a single anomaly, it's in its profound philosophical implications. It forces us to confront the possibility that our universe is not alone, that reality is far grander and stranger than we ever imagined. It represents the ultimate frontier of cosmology, where solid data meets deep speculation, and it showcases the brilliant, creative lengths scientists will go to in order to solve a mystery that refuses to yield to conventional answers. But if neither a supervoid nor a multiverse collision provides a perfect answer, where else can we turn? The beauty of a puzzle this profound is that it inspires truly creative thinking, leading physicists to propose some of the most exotic ideas in all of cosmology. One particularly compelling concept is that of cosmic textures. Imagine the universe in its first moments of existence, a searingly hot and dense medium beginning to cool. As it cooled, the fundamental forces of nature are thought to have separated out in a series of phase transitions, much like water freezing into ice. And just as freezing water can trap air bubbles or form cracks, these cosmic phase transitions could have created defects in the very fabric of spacetime itself. A cosmic texture is one such hypothetical defect, not a hole or a tear, but an intricate knot in the fields that govern reality. If such a texture were to form and then later unravel, the immense energy released would create a powerful gravitational potential, a hill in spacetime. Photons from the cosmic microwave background climbing this hill would lose energy, causing a temperature drop in that specific region of the sky. It's an elegant solution that fits the scale of the anomaly, but the challenge is that these textures are purely theoretical. We have no confirmed evidence they even exist. This leads to other, equally fascinating possibilities. Perhaps the cold spot is the work of primordial magnetic fields, vast, organized magnetic fields that were woven into the universe's fabric in its first second of existence. These fields could have influenced how matter clumped together in that specific region, creating a vast underdensity that then imprinted itself on the CMB. Or maybe it's a clue to a deeper mystery of dark energy. What if dark energy isn't perfectly uniform as we assume? What if it has variations or even different phases? A localized fluctuation in dark energy's strength could have altered the expansion rate of that particular patch of universe, subtly changing how the cosmic microwave background radiation cooled and leaving behind the cold spot we see today. And then, of course, there is always the most straightforward, if disappointing, explanation that it's all a statistical fluke. Perhaps the cold spot is simply a grand cosmic coincidence, a rare random fluctuation that, while incredibly unlikely, isn't impossible. Yet, with each new and more precise map of the sky, from the Planck satellite to future observatories, this possibility becomes harder to swallow. The cold spot persists. What's remarkable is that each of these theories, from cosmic textures to exotic dark energy, requires physics beyond our current standard model. This anomaly isn't just a curiosity, it's a potential beacon pointing toward entirely new laws of nature, forcing us to confront the limits of our understanding and daring us to imagine what might be missing from our picture of the cosmos. Studying the cold spot is a bit like trying to read a faded, ancient inscription from 3,000 meters away while someone shines a flashlight in your eyes. The challenges are immense and begin with the most fundamental issue, its sheer distance. This anomaly isn't in our cosmic backyard. It's a staggering 3 billion light-years away. This means the light and radiation we're collecting from it today began its journey to Earth 3 billion years ago, when our planet was a vastly different place and single-celled life was just beginning to emerge. We are not observing the cold spot as it is now, but as it was in a deeply ancient past, adding a massive layer of interpretive complexity to our analysis. Then there's the problem of the signal itself. We are not dealing with a brilliant beacon in the sky. The temperature difference we're trying to measure in the cosmic microwave background is on the order of 70 microkelvins, an almost unimaginably tiny variation. Detecting this is like trying to measure the heat of a single candle on the surface of the moon from your backyard. It requires instruments of breathtaking sensitivity. Astronomers must rely on indirect methods, painstakingly counting the number of galaxies in that direction to see if there's a corresponding void, or mapping the subtle distortions in the light from more distant objects caused by the gravitational field of the region. Each of these techniques requires massive, time-consuming surveys of the sky, sifting through data from millions of galaxies just to characterize one single, enormous anomaly. Compounding these issues is the contamination from our own cosmic neighborhood. Our view of the cold spot, which lies in the constellation Eridanus, is partially obscured by the foreground of our own Milky Way galaxy. Dust, gas, and the general glow from within our own spiral arm can create their own microwave signals, effectively creating a veil of static that must be digitally peeled away from the pristine data of the distant universe. Scientists have to develop incredibly sophisticated computer models to account for and subtract this galactic interference, a process that is as much an art as it is a science, and one that always leaves a margin for error. Despite these formidable obstacles, the scientific resolve to understand this mystery has only grown stronger. Projects like the Atacama Cosmology telescope, perched high in the dry Chilean desert to avoid atmospheric moisture, are dedicated to mapping the CMB with ever greater resolution. These efforts are slowly chipping away at the uncertainty, providing sharper data that allows us to better distinguish between a vast, empty void and something even more exotic. The very difficulty of the task underscores its importance. A puzzle this hard to solve likely holds the key to a truly profound discovery, pushing our technological capabilities to their absolute limit in the pursuit of cosmic understanding. Thankfully, the very tools we need to cut through this observational fog are now coming online, heralding a new golden age of cosmic cartography. We are no longer limited to staring at a blurry photograph. we are assembling an orchestra of next-generation observatories, each playing a different part to bring the cold spot into perfect high-definition focus. Leading this charge are instruments designed to see the universe in two completely different yet complementary ways. First, we have the galaxy mappers. The Vera C. Rubin Observatory, currently under construction in Chile, is a behemoth in this category. Its sole mission is to conduct a decade-long, ultra-deep movie of the southern sky, cataloging billions upon billions of galaxies with a camera so large it takes over 3,000 megapixels to capture a single image. For the cold spot, this is a game-changer. Rubin will allow astronomers to conduct the most precise galaxy census ever within that 3 billion light-year distant region. If a supervoid is responsible, Rubin won't just suggest it exists. It will map its exact boundaries, density, and structure in meticulous detail, finally testing whether even the largest conceivable void could account for the profound temperature drop. But what if Rubin looks at that patch of sky and finds it's not as empty as we thought? What if the galaxy count is surprisingly normal? That would be an earth-shattering result, effectively ruling out the supervoid explanation and forcing us to lean even harder into those more exotic theories. And that's where the second type of instrument comes in, the CMB refiners. While Rubin maps the present-day structure, facilities like the Simons Observatory, a new array of telescopes also in the high Chilean desert, will peer back to the universe's infancy with razor-sharp clarity. These instruments are the successors to Planck, designed to measure the faint whispers of the cosmic microwave background with several orders of magnitude more sensitivity. They will scrutinize the cold spot's precise temperature profile, its polarization, and its subtle patterns in a way we've never been able to before. The data from Simons could reveal telltale signatures hidden within the cold patch-specific patterns in the light's polarization that could point directly to a cause, whether it's the unique fingerprint of a cosmic texture's gravitational influence or some other primordial phenomenon. But perhaps the most transformative tool isn't a telescope at all, but the software that interprets the deluge of data they produce. The amount of information flowing from Rubin, Simons, and the James Webb Space Telescope is so vast that no team of humans could ever hope to analyze it manually. This is where artificial intelligence and machine learning step in. Scientists are now training sophisticated algorithms to sift through these enormous datasets, not with a predetermined idea of what to look for, but with the ability to identify subtle correlations, anomalous patterns, and weird outliers that a human might easily overlook. It's like having a million tireless research assistants working in tandem, and they might just spot a crucial clue buried in the noise, a strange distribution of galaxies, an unusual gravitational lensing effect, or a statistical quirk in the CMB that points the way forward. This powerful combination of deep, wide surveys, ultra-sensitive CMB measurements, and intelligent data analysis is turning the cold spot from a static, puzzling photograph into a dynamic field of investigation. We are no longer just looking at it, we are beginning to probe it, to test it, and to ask it very specific questions. With these technological marvels at our disposal, we are not just hoping for an answer, we are systematically building the tools that will demand one. So why does this one particular cold patch, billions of light years away, matter so much to the scientists who study it? The answer is that the cold spot is far more than a simple anomaly. It functions as a critical stress test for our most fundamental theories of the cosmos. It's a cosmic courtroom where our established models of the universe are put on trial, and the verdict could change everything we think we know. If the most straightforward explanation turns out to be true, that this is an immense supervoid, then it immediately creates a massive problem for our understanding of how the universe structures itself. According to the standard model of cosmology, which has been remarkably successful, matter should be distributed in a way that makes a void of this scale and emptiness almost statistically impossible this late in the universe's history. Its existence would force cosmologists back to their chalkboards to figure out how gravity and dark matter could have sculpted something so vast and so empty, potentially revealing new properties of these invisible forces that have so far eluded us. On the other hand, if the void explanation falls short and we are forced to consider more exotic ideas, the implications become even more profound. Should evidence ever point toward the multiverse hypothesis, it would arguably be one of the most significant discoveries in the entire history of science. It would provide the first tangible, observational clue that our universe is not alone, but is merely one bubble in a grand, perhaps infinite, cosmic foam. This wouldn't just be a new chapter in a textbook. It would require us to rip out the entire introductory chapter on reality itself and write a new one. Our understanding of physics would have to expand to encompass the laws that govern not just our cosmos, but the relationships between cosmos. It would transform cosmology from the study of a single universe to the study of a multiverse, opening up philosophical and scientific questions we are only just beginning to formulate. Beyond these two headline possibilities, the cold spot serves as a powerful probe for other great mysteries. It tests the limits of our theory of cosmic inflation, that period of faster-than-light expansion in the universe's first moments. Did inflation happen exactly as we think, smoothly and uniformly, or could the cold spot be a relic of a more complex, multi-stage process? It also interrogates the nature of dark energy, the mysterious force accelerating the universe's expansion. Is dark energy perfectly uniform across space, as we assume, or could it have variations? A localized fluctuation in dark energy's strength within the cold spot region could explain its peculiar properties, challenging the foundational assumption that the cosmological constant is indeed constant. This is why the pursuit to understand this anomaly is so relentless. Resolving this mystery isn't about checking a box on a list of cosmic curiosities. It's a direct path to potential Nobel Prize-winning insights. It represents that rare opportunity for a paradigm shift, a moment where the data forces us to abandon a comfortable theory and embrace a new, more complete picture of reality. And perhaps its most valuable lesson is a humbling one, that the universe, in all its majesty and complexity, is still full of profound surprises. It reminds scientists and the public alike that the map of reality is still unfinished, with blank spaces that whisper of discoveries yet to be made, ensuring that the sense of wonder that drives exploration remains forever alive. Yet the true power of the cold spot as a cultural touchstone lies in its educational value. For teachers and science communicators, it's a near-perfect teaching tool, a single mystery that opens the door to a whole curriculum of cosmological concepts. It provides a compelling reason to explain the cosmic microwave background, not as an abstract idea, but as a real, mappable fossil light that holds secrets. It makes the theory of inflation tangible, transforming it from a complex mathematical model into a dramatic story of the universe's frantic birth, a story that might include collisions with other realities. Most importantly, it offers a masterclass in scientific skepticism, the journey of the cold spot from its discovery through the confirmation of its existence to the ongoing battle between mundane and extraordinary explanations perfectly illustrates how science actually works. It's not about proving wild ideas right. It's a meticulous process of debate, evidence gathering, and the gradual, often frustrating, elimination of wrong answers. This dynamic creates a beautiful tension. On one side, you have the thrilling, speculative headlines that call it a universe killer or a doorway to another dimension, capturing attention and sparking the initial "what if?" That draws people in. On the other, you have the measured, cautious language of researchers who remind us that extraordinary claims require extraordinary evidence, teaching a vital lesson in critical thinking. This balance is the heart of its public appeal. The cold spot doesn't just give us an answer, it lets us experience the suspense of the question. It allows everyone, from a PhD cosmologist to a high school student, to engage with a real-time scientific mystery, to weigh the theories for themselves, and to feel the awe of staring into a profound cosmic unknown, reminding us that the universe's greatest wonders are often its most puzzling questions. If this deep dive into the cold spot has ignited your curiosity, and you're eager to follow along as this cosmic mystery unfolds, you're in luck. We live in an era where the frontier of scientific discovery is more accessible than ever before. The journey to understand this anomaly is happening right now, and you can be a front-row observer to every new development. Your first and most reliable stops should be the official sources where raw science is published. The NASA website is an incredible repository of press releases, mission updates, and easy-to-understand articles that break down complex findings. For those who want to get even closer to the cutting edge, the RZIV website, pronounced archive, is essential. This is a free, online repository where physicists and astronomers upload their research papers before they undergo formal peer review. Here, you can read the very first drafts of discovery, the initial arguments and data analyses about the cold spot, often months before they appear in formal journals. Speaking of journals, publications like Nature and Science are the gold standards. While their articles can be highly technical, they also publish superb summary articles and editorials that distill the essence of a new finding, making them a great way to stay informed on major breakthroughs. But maybe you prefer to learn on the go or through more visual mediums. Thankfully, the world of science communication has you covered. Podcasts like Neil deGrasse Tyson's Star Talk expertly blend entertainment with education, often hosting the very researchers who are probing mysteries like the cold spot. On YouTube, channels like PBS Spacetime offer deep, nuanced dives into cosmological concepts, using stunning visuals and clear explanations to unpack the physics behind the headlines. These creators are masters at translating complex mathematics and theory into something profoundly engaging and understandable, and don't underestimate the power of community discussion. Online forums, particularly the Cosmology subreddit on Reddit, provide a vibrant space for dialogue. There, you can find a mix of enthusiastic amateurs, graduate students, and even professional cosmologists debating the latest papers, critiquing methodologies, and offering their own interpretations. It's a fantastic way to see the scientific process in action, not as a dry, monolithic institution, but as a living, breathing, and often wonderfully contentious conversation. As you immerse yourself in these resources, it's crucial to carry with you a key principle of the scientific mindset: intellectual flexibility. Our understanding of the cold spot is not set in stone. It is a working hypothesis, a story that is being rewritten with every new observation. The data from the Vera C. Rubin Observatory or the Simons Observatory, which we just discussed, could arrive next year and completely overturn the leading theories. What we think is evidence for a supervoid today might be revealed tomorrow as an instrumental artifact, or conversely, a puzzling piece of data that seemed like noise might suddenly be recognized as the crucial clue pointing toward a cosmic texture. This isn't a weakness of science, it's its greatest strength: the willingness to be proven wrong, to adapt models to fit new evidence, is what allows our knowledge to inch closer to truth. By following this story with a critical yet open mind, you'll gain so much more than just facts about a cold patch in the sky. You'll develop a deep appreciation for the dynamic, self-correcting, and ultimately human endeavor of science itself. You'll witness the evolution of an idea in real time, a process that is far more dramatic and inspiring than any single conclusion could ever be. So where does that leave us after this journey to the edge of the observable universe and the very limits of our physics? The cold spot endures, not as a problem to be solved by the end of this video, but as a profound question that remains beautifully, tantalizingly open. It stands as a powerful reminder that for all our knowledge, for all our advanced technology and brilliant theories, the cosmos is still capable of presenting us with mysteries that defy easy explanation. This isn't a failure of science, it's the very essence of it. The universe whispers a riddle, and we are compelled to listen, to gather our tools, and to seek an answer. This particular riddle, etched into the oldest light we can see, challenges the core of our cosmological models. It asks us to reconsider what we know about the distribution of matter, the nature of the Big Bang, and perhaps even the fundamental structure of reality itself. Whether the ultimate answer turns out to be a supervoid of unimaginable scale, the ghostly signature of a cosmic defect, or the mind-bending evidence of a multiverse, the pursuit of that answer is already expanding our understanding. It forces innovation in our technology, creativity in our theoretical models, and humility in our perspective. The cold spot, in its vast and silent chill, teaches us that the unknown is not something to be feared, but to be explored with relentless curiosity and awe. It invites every single one of us to look up at the night sky and remember that we are part of a story that is still being written, a cosmic detective story where the next clue could be hiding in the next set of data, waiting to be found. Thank you so much for exploring this deepest of voids with me. If these cosmic journeys spark your curiosity, please like this video, subscribe to the channel, and share your own thoughts and questions down in the comments below. I'll see you in the next video.